Hi everyone, my name is Bruna, and in this semester I worked with Camila to build a posture monitor device as our final project for the Modern Biomedical Technologies class. The idea behind our project is very simple. We know that most of us slouch without realizing it, and we wanted to build a prototype of something that could catch that in real time and alert us before that can become a problem in the future. Well, and why did we choose this topic? Because after doing some research, we noted that 80% of people will experience back pain at some point in their lifetime. On average, we spend 6 to 8 hours a day sitting, and tilting your head forward by just 60 degrees puts an enormous amount of strain on your neck. The core problem we wanted to solve is that most people don't realize they're slouching until they're already in pain. There's no real-time system in everyday life reminding you to fix your posture before damage occurs. And that's exactly the gap we wanted to fill with this prototype. So, our goal was to build a wearable device that can detect bad posture in real time and alert the user through vibration. Here's how it works. A sensor is placed on the body and measures the tilt angle. The user holds a button to set their good posture as a baseline. From that point on, the system continuously compares the current angle to that baseline. If the deviation exceeds 5 degrees for more than 1 second, an alert is triggered and the motor vibrates to notify the user. So now let's take a look on how we actually created this system. On the right, you can see a list of our main components, and on the left, you can see a picture of how everything looked like once it was assembled. So basically, the system was built around an ESP32 microcontroller, which is basically the brain of our device. We use an MPU sensor to detect movement and tilt. For the alerts, we have an LED light with a 220 ohm resistor and a coin vibration motor. To safely drive the motor without damaging the ESP32, we use a 2N2222 transistor and a 1N4007 diode for protection. And finally, we also have a push button that handles the calibration of the device. On the previous slide, we discussed about our hardware. Now we're going to talk about our code logic. So the code runs in a continuous loop with 5 key steps. First, every 50 milliseconds, the MPU gives us X, Y, and Z acceleration values, which we convert through a mathematical function into a single angle in degrees. Then, when the user holds the button for about 1 second, the angle is saved as a good posture baseline, and the LED blinks 3 times to confirm. Then, on every reading, the baseline is subtracted from the current angle to get a delta. This delta tells us how far the user has drifted from a good posture. Then, if that delta exceeds 5 degrees, a timer starts, but only trigger an alert if the user stays out of position for a full second. So in that way, brief movements don't cause false alarms. And then finally, once that second is up, the LED turns on and the motor vibrates. The moment the user is able to correct their posture, everything resets immediately. So now, let's take a look at our actual code. At the top, we define our 3 pins. 18 for the LED, 19 for the button, and 23 for the motor. Then we have our 3 key tuning parameters, which are the threshold angle set to 5 degrees, the hold time set to 1000 milliseconds, and the sampling interval of 50 milliseconds. This means our system is checking the posture 20 times per second. Finally, at the bottom, we can see a function called pitch from accel, which is our mathematical function that takes the X, Y, and Z accelerometer values and uses this function here to convert into a one single angle in degrees. This is basically what tells us how tilted the sensor is at any given moment.
The main idea in this slide is how the device decides when posture has actually become a problem. First, it reads the current pitch angle from the sensor. Then it compares that value to the baseline angle saved during calibration, which represents the user's correct posture. And the difference between those two values is the delta. If that delta is greater than 5 degrees, the device still does not alert right away. It starts a timer first. That delay is important because it prevents small or quick body movements from causing false alerts. Only when the person stays beyond that threshold for at least 1 full second does the system classify it as slouching. At that point, the LED turns on and the vibration motor activates. That makes the system more realistic for daily use because it focuses on sustained back posture rather than every little movement. The serial monitor output helped confirm that the system was working the way it was expected. At the beginning, it shows that the MPU sensor is connected and ready. After the user presses and holds the button while in a correct posture, that position is stored as the baseline. From there, the program keeps printing the current pitch, the baseline, the delta, and whether the system considers the posture safe or not. In this example, the pitch increases enough that the delta becomes much larger than 5 degrees. After that condition remains true for more than a second, the monitor prints slouch detected, which means that the alert has been triggered. When the user corrects their posture, the system prints posture OK, and the alert stops. This output was useful because it let us each see the step of the logic happening in real time. In the following video, we're going to see how the circuit responds in real time when posture changes. When a slouch or major angle change is detected, the motor starts vibrating, and once the user corrects their posture, it stops. That immediate feedback is one of the most important parts of the design, because the user does not need to look at a screen to know if they should adjust it. The design is also meant to be wearable, so the wires would be enclosed along the back and the motor would sit close enough to the skin for the vibration to be felt clearly. Even though this is still a prototype, the demonstration shows that the system works not only in code but also physically. The results showed that the device successfully detected posture changes in real time. It was able to calibrate a good posture baseline and compare all new recordings against that reference. When posture deviated by more than 5 degrees for at least 1 second, the system triggered the alert as intended, and the vibration motor gave immediate feedback, which made the prototype simple but effective. Overall, this project showed that a low-cost wearable device can improve posture awareness and help reduce sustained slouching. Even though it is still an early prototype, it demonstrates that the concept works. For our future work, there are several ways that this project could be improved. Right now, the device mainly monitors one angle, so it works best for detecting forward slouching but not more complex posture problems. The placement of the sensor can also affect the accuracy, and the system currently depends on manual calibration by the user. Another limitation is that it does not store data, so it cannot track posture habits over time. A next step would be adding a battery-powered enclosure so the device becomes fully portable. It would also be helpful to use a gyroscope fusion or filtering for most stable angle measurements. And another improvement would be detecting posture errors in multiple directions instead of only pitch. Adding Bluetooth and a mobile app could also make it a long-term posture tracking possible. And personalized thresholds could make the device more effective for different users. Those improvements would make the prototype more advanced and more practical for real-world use.